Talking about standard cell potentials. Start with the problem here with copper. Copper is going to go from no charge to Cu2 plus. Then we're going to have hydrogen as a standard electrode, 2 plus, form into hydrogen gas on the other side. So to balance this out, to figure out what's oxidized and what's reduced, we're going to add electrons to it. 2 electrons have to be added to the right side to balance the charge. On the other side, we're adding 2 electrons here, so the electrons are balanced out. So by definition, the hydrogen is gaining electrons, so this is the reduction side. Copper is losing electrons, it's the oxidation side. So if we want to figure out if this is spontaneous or not, we need to find out if the E of the cell is positive or negative. So the E of the cell, under standard conditions, is going to be the E of the reduction, which in this case is going to be 0 because it's the She, the standard hydrogen electrode. So it's E of the reduction minus the E of the oxidation. So if you look up the table in your chart, the standard reduction potentials, copper is 0.34 volts. So the E of this cell under standard conditions is going to be negative 0.34. So in that case, since this is a negative value, this is not spontaneous because the E of the cell is not positive. Now, how this works with the activity series, so we can think about how this works in terms with spontaneity in general with the Gibbs free energy. When we think about electrons and what metals want to be oxidized, there's an activity series we talked about in chapter 4. That means the element really wants to lose electrons really quickly. So those are the elements that really want to be spontaneously to give up those electrons. When you look at Gibbs free energy itself, this is the base Gibbs free energy. Delta G is the measure of the free energy allowed to do work. If you remember delta H, that is the enthalpy of the reaction. T is the absolute temperature that has to be in Kelvin, and that the entropy is the disorder of the system. So in this case, if delta G happens to be negative, that means it's spontaneous. So the delta G would have to be negative, then it would be spontaneous in that to happen. When we think about a redox reaction is spontaneous by using this equation. Delta G is equal to negative NFE. N is the moles of electrons. So like in our previous example, there were 2 electrons transferred, so that value for N would be 2. F is Faraday's constant. A couple different values for it. It could be 96,485 coulombs per mole, or it could be 96,485 joules per volts per mole. You can see either one. Big thing to think about in this is that is that delta G, if it's negative, is spontaneous, and E has to be positive to be spontaneous. You can also calculate K from any of these equilibrium expressions. The graphic I'm about to show you does a really nice job of showing all those different conversions. So if you notice here, if you know delta G, if you want to find delta G, if you know the E standard of the cell, you can plug that into the equation and solve it. If you want to find out what the equilibrium constant is, and you know delta G, R is one of the gas constants that you can use. That's helpful. T is the absolute temperature. And you can solve for E of the cell if you know the equilibrium constant and with the Faraday's constant as well. That kind of is the pattern of how you want to solve those whenever you work them out. So again, delta G needs to be negative for it to be spontaneous. You also need the E value to be positive to be spontaneous. So, sample problem on the back of your sheet talks about how we can do this and how we can calculate this. So we're going to use standard cell potentials in table 20.1 to try to calculate the standard free energy for delta G. So the first step that we want to do in any redox reaction is we want to break it down into its parts. So we're going to have 4Ag solid. It's going to break into the other side 4Ag plus. So that's one of the half reactions. And then the other half reaction, we're going to see O2 break into to H2O. And then if you think about balancing all this out, when you sit balancing the hydrogens out, we can add water. So we have to add 4 waters to this side to get that to balance. So we have 4 H2 pluses there, 2 H2Os. In terms of acidic solution, on the top of this, when you think about the H pluses that you've got, trying to balance it out, we have I need 2 of those, 2 of the waters. We do 2 of the waters, we end up with 4 on that side. Charge-wise, we have 4 hydrogens, and then try to balance the charges out for this. We ended up with our 4H pluses. Sorry. This has got to be 4H pluses on the top of this. So we already have the waters balanced. So it's got to be 4H pluses plus O2. So then we balance out the electrons in all of this. We've got to add 4 electrons to this side to balance out the charge. And then we have to balance out on the other side. We have to add 4 electrons to this side to balance it out. So we've kind of figured out what's oxidized. We figured out what's reduced. Everything's balanced that we've got. Didn't say it was in basic solution. They told us it's at standard conditions. So we can find out what delta G is first. So if we want to find out delta G in this problem, delta G is going to be equal to minus NF and then the standard cell potential of what's going on. That's how we find delta G. So we know several parts of this. We know what N is. There are 4 electrons that are transferred. So 4 would be N. Faraday's constant, we also know what that is. Faraday's constant in this problem, we're going to use the 96,485 joules over volts times moles. And then we can find out what the standard cell potential is of this reaction by doing what we have been working with in the past. So the standard reduction potential, reduction is gain, and we're dealing with oxygen in this case. When we look at the value for each of them, the reduction or the reducer, that value for this E value is 1.23. And then on the top, looking at the silver value, it's 0.80 when you look at it on the chart. So when we find the E of the cell is going to be those values. When you solve them, it's E of the reduction minus E of the oxidation. So it's 1.23 minus 0.80. So that equals the E of the cell ends up being 0.43 volts. So that is positive. So that makes sense that this should be spontaneous right now to try to calculate, but we want to know how much energy that is. So when we work back up here to delta G, we're going to plug into our equation then. So we're going to have minus 4 times Faraday's constant, 96,485 joules over volts times moles. We'll put that in brackets, we keep it straight. And then we've got our E of the cell, which is 0.43 volts. Now multiplying that together and trying to solve for what that is, notice what units cancel out. We get volts to cancel, and then I have just joules per mole. So when I plug this in for delta G ends up being negative 165954. In terms of the units, if you try to think about how the units work, you've got joules per mole. Now notice that it's negative, so yes, spontaneous, and that's the free energy that's allowed to do work. Now once you've solved that and you found out what delta G is, you can also find the equilibrium constant as well by using this, the other equation that we saw earlier. So we'll move this up. Remember that the other equation that we had earlier was delta G is equal to minus RT times the natural log of k. So we know in this problem, we know all these different parts of it because we know the delta G is negative 165954 joules per mole equals minus the ideal gas constant, 8.314 in this case, and that's joules over moles Kelvin. We'll put that in brackets. Keep the negative outside of that. And then the absolute temperature, they told us it was standard conditions, so that's 298 K times, I'll put that in brackets, the natural log of the equilibrium constant. So now all I have to do is solve for the equilibrium constant in the problem whenever I get finished. When you do all the algebra of this, you end up dividing two negative terms by each other. So you end up with a positive value when you get finished. And you should end up with 69 equals the natural log of k. And to undo that natural log of k, you're going to raise, and to undo the natural log, it's going to be e to the x to both sides, e to the x over there, once you solve it. And when you find that, you find out that k is going to be equal to 9 times 10 to the 29th once you solve that. That's a huge value for equilibrium. That makes sense that it's spontaneous, wants to go in the forward direction, and you can identify how large the value is whenever you're solving for k. So you can use Gibbs free energy to help figure out if it's spontaneous. You can figure out how it looks in terms of the problems for solving. We'll talk a little bit more about this in class.